Hello, my name is Ben Josephson. I'm a student at the University of North Dakota in the Distance Engineering degree program, and this is my Signals and System project on AM modulation, receiver and transmitter simulation using LabVIEW software. The idea for this experiment came from a desire to find a way to put together all the concepts that we've learned over the course of the semester. This project involves the concept of signal generation, representation in time and frequency domain, convolution of signal, sampling and reconstruction of signals, aliasing of signals, and also filtering of signals. I wanted to find a project that would touch on all those topics and help to illustrate some of those topics so that I could better understand the process behind them. So, to better understand AM modulation, I went to the NI website and looked at some of the information they have there and came across a project for the development of a AM modulator, which is shown here. And the idea behind AM modulation is that information containing signal can be modulated with a higher frequency carrier signal that can carry that information over longer distances. And then when the information is received at the destination, the information is uncoupled or demodulated from the carrier signal and amplified so that it can be effectively communicated. So what we see here is we've got parameters that we can adjust for the carrier frequency, the modulation frequency, the carrier amplitude, and the modulation amplitude. If we run this VI, we set these to some given values. Oops, I didn't want to do that. We'll go ahead and click run. We can create a signal that is modulated, and in this case it's just two sine waves that are modulated together, one carried on top of the other. And what we have here is we have the modulated signal where a sine wave is carried on the side bands of the carrier frequency, this being the carrier signal, and then in the frequency domain we've got the representation of the carrier signal, which is set at, in this case, 1000 Hertz. We can adjust that and we see the right and left shift of the carrier waveform and its side bands. And if we change then the modulation frequency, the width of the side bands increases in the frequency spectrum. Adjustment of the carrier amplitude adjusts the center frequency or the carrier frequency, and adjustment of the modulation amplitude adjusts the frequency or the amplitude of the sidebands, which is where the actual information signal is being carried. So this VI was created to help myself develop a better understanding of the modulation process. So the next project that I decided to take on, which was really the project that interested me in the first place, was to build a VI that could model AM transmitter and receiver. It was a fairly complex project and involved quite a bit of work in LabVIEW, but that was good because it helped me develop my skills immensely. Essentially what we have here in an overview is 3 AM transmitters that are developed. A separate sub-VI was developed, one to create a sinusoidal signal, one to create a dual sinusoidal signal, and one to create a triangle signal. These VIs could take a frequency input so that that signal could be generated at a specific low frequency. We then introduce a AM modulation VI, which does the process of modulating the signals, summing them together, and multiplying by a carrier frequency to put that carrier frequency up and transmit that signal on a waveform at a higher frequency. We then sum all the signals together so that we can create the transmission that would simulate the signal being broadcast over the airwaves on an antenna. The second stage then brings in the AM receiver, which receives the signal on the antenna. We use a tuner coupled with a bandpass filter. The bandpass filter, again, is another sub-VI The idea of the bandpass filter is that we can narrow down a range within where that the carrier frequency lies, and decrease or attenuate the signals outside of that range. It gets rid of some of the interference and the noise. We then multiply that signal by a local oscillator signal, which is the same sinusoidal signal that we're using for the carrier frequency. When we multiply those two waveforms together, we get a sum and a difference, and we're able to filter out the carrier frequency and extract the sidebands which contain the information. We do generate some additional frequency noise in this process, so we use a second bandpass filter to attenuate the unwanted signals. We then take the positive frequency here. We go through a low pass filter which gets rid of all of the high frequency reproductions of the signal that would cause interference. And finally, in the amplification stage, we block out the average DC signal that is a result of the carrier wave in order to clean up our actual messenger frequency. And then in this case we go to the spectrum and the time domain. We've created system constants here that are global variables for the intermediate frequency that we use, the maximum frequency, the sampling frequency, and also our time duration. They were created as global variables so that they could be referenced in all of the sub-VIs and also in this main VI. The output then goes through a viewer VI, which is set up to isolate the frequency spectrum and also the time domain. So this works similar to the VI that we used for the modulation itself, but instead of using express VIs built in LabVIEW, we simply created our own. This is all enclosed in an event structure so that by adjusting the tuning knob, you initiate the VI to run. So I will bring up the VI itself, and here you can see it takes a little bit to tune this, so I've pre-tuned it. You can see that with our filters enabled, we have a frequency being broadcast here on 3700 Hertz, which corresponds to our double sine wave carrier frequency, and as you can see, the time domain signal we pick up matches the double sine signal that we're broadcasting. If we run this VI, we take out the filtering, and you can see all of the different aliases that are out there that are being broadcast, and we have a very messy signal that's being received. But if we enable our bandpass filters, we can start to clean up some of those extraneous frequency signals that are outside our frequency of interest, and we start to get a clear signal coming through. Here, we've still got some noise, but if on the high frequency end, so we have some spikes that are outside the range we're looking for, but if we enable our low pass filter, we're able to clean up that signal, and now we can start to hone in on those specific frequencies that carry the information that we're looking for. And in this case, we can tune back in on, looks like we've focused in on a triangle frequency here. So overall, this was an interesting project that really developed my knowledge of LabVIEW, because I had to learn to use a lot of functions that I didn't know much about in order to make some of these calculations. It also helped to tie together all of the concepts that we've studied over the course of the semester, and it was really nice in the fact that it illustrated the concepts, it put them all together, and it put them in a process that allowed you to actually see the effect once the system was implemented. So thank you very much for your attention, and that concludes my presentation.